The UAI results are finally out, confirming what many of us feared in our own labs. The newest flagship chips promise to revolutionize inference, yet they delivered disappointing latency numbers for critical workloads. You clicked this video because you need to understand why your hardware ROI is plummeting despite having more raw power on paper than ever before. By the end of these minutes, I will explain exactly how theoretical benchmarks mislead production planning and reveal a counterintuitive reason why legacy silicon often outperforms modern giants in real-world scenarios. Here is the thing that keeps junior engineers up at night. We are obsessing over FLOPS, or floating point operations per second, as if it were the only metric that matters for artificial intelligence hardware. It feels logical on the surface because higher numbers usually mean better performance. But when you move from a benchmark suite to actual production inference, that single number becomes dangerously misleading. The industry has fallen into a trap where we optimize for training throughput while ignoring the brutal realities of latency and cost efficiency during deployment. Let us look at the data driving this confusion. Research indicates that high-performance flagship chips frequently underperform legacy hardware in specific workloads due to a fundamental disconnect between peak benchmark metrics and actual inference latency. The theoretical FLOPS benchmarks ignore the memory bandwidth bottleneck and data movement costs, causing those shiny new processors to choke when faced with real-world demands. In modern architectures, compute cycles are often wasted waiting for data to arrive from memory rather than processing it. This means a chip with half the peak FLOPS can actually finish an inference task faster if its memory architecture is better aligned with your specific model. Consider how sparsity patterns and quantization requirements dictate production efficiency. Generic high-FLOPS silicon often wastes power on dense operations that legacy, specialized accelerators handle more efficiently. When you deploy a large language model like OPT-175B or similar architectures in the wild, they do not run as dense mathematical matrices every single time. They rely heavily on sparse activations and quantized weights to reduce memory footprint. If your new flagship chip is designed for maximum throughput of dense matrix multiplications without accounting for these sparsity patterns, it will burn through energy while sitting idle waiting for data that does not fit its pipeline efficiently. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates what we can call the newest chip fallacy. It arises from optimizing for training throughput rather than inference latency, leading to architectures that introduce significant overhead such as complex interconnects or memory hierarchies. These complexities degrade performance for smaller, specific production models where simplicity is king. The newer chips often have sophisticated software stacks and runtime environments designed to manage massive parallelism across thousands of cores. But when you are running a single inference request on a model that does not utilize all those cores simultaneously, the overhead required to coordinate them becomes a drag rather than an asset. You might wonder if this is just about bad design or flawed evaluation methodologies. That brings us to a critical counter-perspective from Google DeepMind regarding their work with alpha chip and TPU generation. Their research challenges the narrative of inherent AI hardware failure by demonstrating that alpha chip has successfully generated superhuman layouts for 3 generations of TPUs and Axion CPUs. This evidence suggests that perceived failures often stem from flawed evaluation methodologies rather than the hardware itself. For instance, omitting essential pre-training steps or using unrepresentative test cases can make a perfectly capable chip look like it is failing to deliver results in isolation tests. However, we must acknowledge where real failure occurs beyond just testing flaws. General AI system surveys highlight that while large models have faced significant operational outages, these are largely software-level resilience issues rather than fundamental hardware defects. The problem is often not the silicon itself, but how we integrate it into a larger ecosystem. When you prioritize FLOPS over latency and cost efficiency without rigorous, representative production testing, you set yourself up for disappointment before deployment even begins. The lack of accessible, specific case studies on incidents like the so-called million-dollar chip mistake creates a knowledge gap that forces us to rely on broader failure analysis frameworks. We see patterns where hardware adoption shows legacy chips maintaining higher utilization rates in production because their fixed-function pipelines reduce software stack complexity and runtime overhead. New flexible architectures promise adaptability but often come with unoptimized code paths that slow down execution when the workload shifts slightly from what was intended during design time. Cost efficiency in production is a function of total cost of ownership, including power and cooling, where the energy per inference of a lower FLOPS legacy chip frequently beats a high FLOPS flagship due to thermal throttling or inefficient memory utilization. The newer chips often require aggressive cooling solutions that add massive operational costs, which are rarely factored into initial purchasing decisions based solely on benchmark scores. If your data center is running hot and you cannot sustain peak performance without throttling, those impressive FLOPS numbers become theoretical artifacts rather than practical tools for generating revenue. This brings us to the core realization we need to take away from this discussion. The mistake is not necessarily the chip's raw power, but the industry's tendency to prioritize FLOPS over latency and cost efficiency without rigorous, representative production testing. When you evaluate hardware based only on peak theoretical performance, you ignore the nuances of memory bandwidth, data movement costs, and architectural overhead that define real-world success. You end up buying a Ferrari for city traffic when a reliable sedan would get you to your destination faster and cheaper every single time. The solution lies in shifting how we approach hardware selection for production environments. We need to move away from chasing the highest FLOPS numbers and start measuring actual latency per inference, energy consumption per token generated, and total cost of ownership over the lifespan of the deployment. This means running representative workloads on candidate chips before signing any contracts or committing capital. It requires understanding that a chip designed for training massive models might be terrible at serving those same models in production if it lacks the necessary memory bandwidth or introduces too much latency overhead during inference. As you move forward in your engineering careers, remember that benchmarks are guides, not gospel. The most successful engineers will be those who look past the marketing numbers and understand the physical constraints of their systems. They will ask how data moves through memory hierarchies and whether sparsity patterns can actually be exploited by the architecture they choose. By focusing on these practical realities rather than abstract performance metrics, you ensure that your infrastructure delivers value where it matters most, in production environments serving real users with consistent reliability and reasonable costs. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.